In this lesson, we'll uncover the principle of maximum power transfer, one of the most important concepts in circuit analysis. You'll learn how internal resistance and load resistance determine power delivery, along with how to quickly analyze both the voltage source and current source circuit. So let's jump right into it, shall we? In order for us to investigate the power transfer between a practical source and a load connected to it, let's take a look at this diagram. So here we have a constant voltage source with a known internal resistance, R sub S, and that's connected to a variable load resistance, R sub L. When the variable load resistance is zero, it is called a short circuit, in which case the load voltage becomes zero and the load current is equal to the voltage divided by the internal resistance. When the variable load resistance approaches infinity, it is called an open circuit, in which case the load current becomes zero and the load voltage is equal to V. One area of interest is finding the value of the load resistance that will absorb maximum power from the source. The power absorbed by the load is shown in equation 1, where we have the power equaling the load current squared multiplied by the variable of the load resistance. The load current can be determined in equation 2 by taking the voltage squared divided by the internal resistance plus the variable load resistance. And by substituting equation 2 into equation 1, we can rearrange the formula as shown in equation 3, where we have the load resistance equaling the voltage squared divided by the internal resistance plus the load resistance, and that's squared, and then that is all multiplied by the load resistance. A problem related to power transfer is that of source loading. The wire diagram on the left represents a practical voltage source, which is an ideal voltage source along the internal source resistance, and that's connected to the load resistance all in series. The wire diagram indicates the internal voltage drop within the source, which depends on the amount of current drawn by the load. The voltage seen by the load voltage is somewhat lower than the open circuit voltage of the source, and when the load resistance is infinitely large, the current goes to zero, and the load voltage is then equal to the open circuit voltage of the source voltage. Hence, it is desirable to have as small as possible internal resistance as possible in a practical voltage source. Now moving to the right diagram, we have a practical current source which possesses an internal current source along with a parallel of the internal resistance connected to a load resistance, and those two are in parallel. The diagram equates to the formula below, where the internal current drawn away from the load because of the presence of the internal source resistance. Thus, the load will receive only part of the short circuit current available from the source. And when the load resistance is zero, the load voltage also goes to zero, and the load current is then equal to the short circuit current of the source. Hence, it is desirable to have a large and internal resistance as much as possible in a practical current source. Alright, you made it to the end. If you found this lesson helpful or learned something new, please consider giving this video a like and subscribing to the channel for more engineering crash course content. Thanks for watching, and I'll see you guys in the next lesson.